Welcome on a Monday morning. Sort of feel more like winter. Not bad. 50s can feel like it's really cold. It's colder than that today, though. Yesterday afternoon it was sunny and in the 50s all afternoon. But it felt colder. I think we're at high elevation, so. Okay. Well, any questions about anything? We're getting started on things. So remember, you need to have your cell phones put away. It's 11 o'clock now, so we'll go ahead and start class. And class study grade. Kind of communicate here a little bit just to make sure people are getting their questions answered. Excuse me. So we got into chapter 7 last time in the last class. Y'all took a test last Monday, and then on Wednesday we got into chapter 7. I haven't finished grading your tests yet. I've graded a lot of your tests though, almost all your tests. So we'll see if I'm able to get those back by Wednesday. Okay. Yeah, we've been kind of using the method of not only no cell phones or headphones, like we said at the beginning of the semester, but also no laptops also, just so we're focused and taking notes and everything. Okay, so we got in last time to talking about looking at distributions of sample means of X bar. It's like a distribution of the sample means where we're taking a lot of samples, all of the same size. And one of the amazing things that happens is if you have if you're taking samples of a size where the sample size is 30 or greater, and you're looking at the means of each of those samples, and each sample is a size of 30 or greater, then that X bar actually has a normal distribution. And we can use methods we used in chapter 6, where we had a normally distributed variable to find out things about the distribution of sample means. And so we use methods similar to what we did in chapter 6 for a normally distributed variable. And so some of the things we talked about that came up in 7.1 was if you know you have a normally distributed variable, then it doesn't matter what your sample size is. If you already know that the variable is normally distributed, it doesn't matter what your sample size is. The distribution of those sample means, we're looking at the sample mean of each of those samples, will be normally distributed. But it also turns out that if you don't know anything about your variable, maybe it's not normally distributed, it could be skewed left or skewed right, or maybe you just don't know. If the sample sizes are 30 or more, sort of the rule of thumb where it seems to work, if the sample sizes are 30 or more, the X bars, the sample means of each of those samples, will be a normally distributed variable. And so we used kind of what we did in chapter 6, very similar. We have to find Z is the number of standard deviations, X bar is from the population mean, and we may not know, and then sigma sub X bar, and so the mean of the distribution of sample means is the same as the population mean. That's one thing we talked about. But the distribution, the standard deviation of the distribution of sample means, sigma sub X bar is the population standard deviation divided by square root of n, where n is that sample size that you're using. Yeah, you're using that. And because of, of this definition and some mathematics, we could find z by doing this. Okay, so we had, I put up 7.1 after class on Wednesday, and I hadn't put up 7.2 yet, but I almost could have. I wanted to do a couple more examples, then we'll go on to chapter 8, and I'll put up 7.2 after class. All right, so let's read, and this will kind of bring back what we do on some of these problems where we're considering the distribution of sample means. Okay, so it says, suppose babies born in a large hospital have a mean weight of 3,758 grams. Okay. Now, if you measure that in kilograms, it would be like 3.7 kilograms. And that's often how you see mass presented, but it's also in, and then the variance is 204,304. Remember, the variance relates to the standard deviation. It's the square of the standard deviation, right? So let's see what we get if you take the square root of this number, because we'll need the standard deviation. Okay, maybe that number is a perfect square, and we'll get a whole number. Let's see. We get 452. All right, 452 is the sigma. Okay. All right. If 89 babies are sampled at random from the hospital, so there's our sample size, n equals 89. So even if we're not taking a whole bunch of samples, if we're just taking one sample, we can still compare that to the distribution of the sample means that, we can kind of think of the distribution of x bar as being part of that distribution of sample means. If 89 babies are sampled at random from the hospital, what's the probability that the mean weight of the sample babies would differ from the population mean by less than 48 grams? Round your answer to 4 decimal places. Okay, so we want to try to figure out what's the probability that x bar, and what's the probability that the mean weight of the sample babies would differ from the population mean by less than 48 grams. So we know the population mean in this case is 3,758. Oh, yeah. So for this, we need to kind of think, not exactly this, we need to think about, if we're considering the probability of this, it would actually be something different from this, actually. So I'm going to put a line through this, but it would be, so if you differed from the population mean by less than 48 grams, what do we get if you, what's 3758 plus 48? Is it 3806? Then what do you get if you subtract 48? You can just do it with a calculator, but I'm going to just go ahead and do this without a calculator. Maybe it's easy enough. And you can always kind of check with that. So really what we want to find is, have to kind of read this carefully, what's the probability that the mean weight of the sample babies would differ from the population mean by less than 48 grams. So we're really talking about x bar being between 3710 and 3806. Does that make sense? Okay. And here, once again, it doesn't matter if you include the equals or not. Since it's a continuous probability distribution, it doesn't matter. We're kind of measuring areas again, like we did in chapter 6, that are in an interval between two numbers. And so the area above any one number is just 0. So you can include the points and write it like this, or you can leave them out, and it's both are correct. Okay, so we need to find the z values for these two. So this is a little bit like what we did at the end of chapter 6 before your last test that you took a week ago. So we have, so x bar, let's write down the formula over sigma sub x bar, and that's going to be x bar is, yeah, so 3710. Well, I guess we kind of know this part. It should check back, right? And then the sigma sub x bar is sigma divided by square root of n. Go ahead and put that in there. And this difference should be negative 48, right? Because that was, yeah. Because we were wanting to know if we're within, the mean weight is less than 48 grams away from the population mean. And then for sigma, we have 452. And then our sample size is 89. And I don't think that's a perfect square. So to figure out the z value, I would simplify this as much as you can. So if you're dividing a number by fraction in this way, you turn that into multiplication by multiplying by the reciprocal. So this would be a little bit easier to put into the calculator without making a data entry error. Because division, when you have two divisions in a row, division isn't associative. So you couldn't just, let me show you. Now this is a good thing to show. So you don't do this. So if you just put all these numbers, dividing, then you had square root of 89. Associative means that you could group the division in this way any way you want, but you can't. You would have to put parentheses around, like we have in the, we'd have to put parentheses around the second one. Now this will be different than what we end up getting. This is negative 0.0112. Yeah, so don't do that. So if you flip and multiply, it should still come out the same. And so let's go back and we'll put in times square root of 89. Now multiplication and addition are associative. And I'm not talking enough about associative, so you may not remember what that means, but it just means you can group it in different ways. You know, like 5 times 3 times 4 is the same as 5 times 3 times 4. So you can group multiplication, and it's the same either way. So you say multiplication is associative, where you can't group division that way. If you just divide by 3 numbers in a row without parentheses, then it's really something different than what we want here. Division is not associative. All right, so if we do it like this, notice this number is going to be different, right? Negative 1.00. Okay, so that's our z value, negative 1.00. Oh, so this may end up being one like you could do using the empirical rule, if it's going to be just one standard deviation away. And then the other z value for the other x value for x bar we're looking at, so that's going to be just using this formula again, 3806 minus the mu. Yeah, that should be the one that comes out to be 48, right? And then we have 452 divided by square root of 89. So that part's the same. And then when you subtract, that should be 48, right? And you can kind of check yourself. And yeah, 42 gets us to 3,800, and then 42, 42, and then 6 is 48. And so if we flip and multiply again, it looks like it's going to be the same thing, except the sign's different, right? So here we're dividing this difference, which is 48, and I went ahead and just did it in fewer steps than I did here, because it really came out to be the same except for that sign. And so this should come out to be 1. Let's see. Not exactly 1. There's some, but to 2 decimal places, it's 1. Let's just make sure that was right. As a double check. Yeah, 1.00. Then the third place is 1, so we round down. So we really could answer this one. You could really answer this one like we did using the empirical rule. So we're really asking, in other words, so let's write this out. the probability that the sample weight of the baby weight is between these two number values for grams is the same as the probability that the z values just one value away from. So really, these weights that we're interested in, this interval of weights really represents one standard deviation away from the mean. So this should come out to be 68%, right? Remember the empirical rule from back in, it was right before your first test, right? What was that, 3.2? But let's see if we did it using the method we'll have to do for a lot of these. Let's remember what that is. That's, if we draw a quick picture, that one standard deviation is like right where that inflection point is. So we're really trying to find this area, right? And we'll just put the z values here, z equals 1, minus 1. You can also put the x values here also, but so we want the area below z equals 1. We want all of that, but we want to subtract out this weight below minus 1, right? So that's how we can write it in terms of, that makes sense so far? So you were doing some of this in chapter 6, but it's a little bit different now that we're looking at a distribution of sample means that came up in chapter 7 just last Wednesday. Okay, so now let's look in the tables. Let's see if we end up with 68%. We kind of know, because these came out to be just one standard deviation, the total answer should be like 68%, or 0.6800. It may be a little bit different now using the tables, but let's see. So probability z less than or equal to -1. We need to think of that as -1.00. So we go to -1.0 on the far left and go over to the column headed by 0.00. We get 0.1587. 0.1587. So we did that one first for some reason. I'm not sure why I did that one first, but yeah, it shouldn't matter. All right, so now if you look at the table B for the positive ones, let's look for 1.0 on the left. And here on this table, 0.00 is right the first column. And we get 0.8413. 0.8413. Now when you subtract those, what do you get? It should be close to 68, because that's really the empirical rule we saw back in 3.2. I'll just subtract it with a calculator rather than write it out a different way. All right. So 68 point. We'll go ahead and take it to those other places, but you can see it's like 68%, right? All right. So 0.6826. And it's set around to 4 places, and that's what those tables give you for the probabilities. The z values are to 2 decimal places. Any questions on that one? Let me see what we're asking again here. If 89 babies are sampled at random from the hospital, what's the probability that the mean weight of the sample would differ from the population mean by less than 48 grams? That kind of confirms that 48% of the babies and or at least the sample of a sample of 89 babies, the sample would differ from the mean, and for 68% of those samples. The mean weight would, yeah. All right. Any question on that one? Okay. All right. Now this is another good one, because this one actually has 2 parts, and it compares what we did in chapter 6 with what we're doing, what's new in chapter 7. So you'll be able to see both of those. All right. So 2, the mean weight of an adult is 69 kilograms with a standard deviation of 11, and 31 adults are randomly selected. Okay. Okay, so that mean weight is the population mean. But that's also the same for the mean of of the of the um, the sampling distribution of the sample means for any particular size sample. It's going to be 69 kilograms. So one of the examples we did 7.1 at the beginning of class. Oh yeah, you can't have your laptops on during class for class study grade. Remember, you need to put it away. Yeah. We're playing that game so that. All right. So the standard deviation is 11, and the sample size is 31. So part A says, what's the probability that a person chosen off the street, not from the sample of 31 adults, will have a weight that differs from the population mean by more than 1.3 grams? Okay. So that's really what you did in chapter 6. So part A is like what you did on the test and in chapter 6. It's like you're taking a sample of one person, just choosing a person off the street. Okay. You're having trouble hearing me? All right, so we'll try that, and it seems to be showing volume, but this one may actually be better. All right, so part A is really just to find, let's figure out what is asking for. What's the probability that a person randomly chosen off the street, not from the sample of 31 adults, will have a weight that differs from the population mean by more than 1.3 kilograms? Okay, so we need to figure out what does it mean to be more than 1.3 kilograms. See, what does that mean? That means that X, so here it's just X, not X bar. X is less than, well, what's 69 minus 1.3? Please have your cell phones put away during class. You know, if you really need your laptop or cell phone, you can just go, you know, watch the recording later. You'll get a 0 today for your class study grade, but you know, you can still do it. You know, I don't. It's a free country. All right. So what's 69 minus 1.3? Too slow. 67.7. I might be wrong, but at least I tried, right? Is that correct or not? Hmm? And what's 69 plus 1.3? You young people are too slow. All right. More than 70.3? Oh, we could include the equal, you know. Huh? Does that seem right? Yeah, get involved. This is your class, so get involved. Take it apart. Tear it up. All right. But get involved. This is not my class. This is not my problem to do. This is yours. But 1.3, I think those, okay, that's what we're looking for, right? Probably a person randomly chosen off the street will have a weight that differs from the population mean by more than 1.3. Okay. Okay, so for this one, we need to find the z value, and this is exactly what you were asked. This is the formula we use for some of those chapter 6 problems. So we need to find the z values for these. And once again, though, these differences should come out to be, we did that right. Is that negative 1.3 over 11? And that's one good thing about this is, well, we needed these numbers sort of in order to write things out. To write out the probability. Seem all right? What do you get if you round this to 2 decimal places? Hmm? 0.118? What is that to 2 decimal places? 0.118. 0.12? Okay. Sounds good. All right. Now this other one is going to be, we can kind of check ourselves that we did that 1.3 calculation correctly. 70.3, is that 1.3? And then over 11, that should come out to be 0.12. All right. So what we can write this then in terms of z values, the probability that z is less than or equal to negative 0.12. Oops, shouldn't put that parenthesis in there. Or z greater or equal to 0.12. Okay. All right. So maybe it's helpful at this point to draw a little picture. We're really kind of looking for 0.12. We'll just put negative 1.2 over here. Negative 0.12. Doesn't matter. It doesn't have to be accurate. Just make sure you get it on the right side of the, the top negative side or the positive side. And then the other one is above 0.12. And so we're looking for those areas. Okay, so now these are mutually exclusive events. Probability of this or that, you can't be below negative 0.12 and also above positive 0.12. So so this probability that we saw from the probability chapter is just the sum of these individual probabilities, right? And now the first probability we can get straight from the table in the back. So let's go ahead and do that. What's the probability of being below negative 0.12? So I guess we'll look for, in table 1, look on the far left for negative 0.1. Can you put your backpack away? And your cell phone? Okay. Yeah. Should I have any reason to trust anybody? No. All right. Negative 0.1. And then you go over to a column headed by 0.02. Like I said, you can go do these things. You'll get a 0 today, you will. But hey, at least you get to play with your cell phone and your laptop, It's not what you paid hundreds of dollars for, I'm sure, though. In terms of, for this class, right? All right, so 0.4522. Yeah, if there's any questions, be sure and jump in there. And then for this one, we need to rewrite this as 1 minus this probability, right? Write it out here a little bit bigger. Oh no, that was positive. My mistake. That should be positive. Yeah, if I left that as negative, that might be a little bit confusing because, all right. So we've got this one, we got this one. These are probably going to be the same, right? Let's check if that's right. When we subtract this from 1, we'll get the same as this one. But let's not, you don't want to assume too much in life and in mathematics. So, all right, so if you look at the probability below 0.12, because we want the probability of being greater than 0.12, we would So 0.1 here. And then if you go over the third column, that's the column headed by 0.02, that's 0.5478. And so, what do you think that's going to be? I bet this one, can we use the rule of nines to do that subtraction? Talked about the rule of nines. We need for the first three digits of our difference, the number that added to 5 gives you 9, and the number added to 4 that gives you 9. What's that going to be? 4 and 5. The number added to 7 gives you 9. And then finally, the one that added an 8 gives you 10, right? And then you add back, and you should get 1, right? All right, so it does end up being just 2 times that first probability. And you almost get that from the symmetry of the normal curve, right? So, is that right? Did I add those up correctly? All right, so it seems like for this one, this is the probability of choosing somebody off the street. Person randomly chosen off the street, not from the sample 31 adults, will have a probability that differs from the mean weight by 1.3 grams either way, either 1.3 grams below the weight or 1.3 grams above the weight of the mean for the, and in a way we say weight, but really grams are used, kilograms are used to measure mass, but you know, when we're on planet Earth, it's really the same thing. You go to the moon though, weight, the mass will be the same as if you're on the Earth, but the weight will be different. That's the difference between mass and weight. Weight really depends on gravity. Gravity on the moon is different. So your weight's going to be different on Earth as the moon, but your mass is the same. You'll still have this, it'll still be this many kilograms. But, you know, we treat them almost the same here on Earth. Earthling. All right. So we got that probability. Now, the second part, so that was like a chapter 6 problem, like from what you did in, well, please put everything away in your backpack and everything and all your nodding, yeah, like, well, show me you understand. Show me. I'm having to wrangle people with, no, I just mean your technology, your cell phones, laptop. Having a little bit of trouble wrangling people, especially the people who should be setting the examples for the other students, right? Just put away your pink backpack. Yeah, put that away. No, the pink, that thing that, yeah, okay. I just.
Can't tell people to move their stuff.
Anyway, we have to stop talking about this because we have other work to do. There are people that didn't pay for this kind of activity. So please help me out. Help your fellow students out, okay? And if you want to earn a class study grade today, I'm trying to be flexible. I know you were working on this class, but I'm trying to be as helpful for people as I can. All right, so now part B, now we're going to see the difference between choosing a sample of one person and choosing a sample of 31 people. Okay, what's the probability that the sample mean will differ from the population mean by more than 1.3 grams? And it almost sounds like they're asking the same question as part A, isn't it? Okay, so for this one, we're looking for X bar. Now compare this. Almost looks like we're setting it up the same way, right? And, but the Z values will be different, won't they? Because we'll have X bar for the mean, excuse me. And then we have, so these differences will be the same. That part will be the same. because we have 67.7. We're wanting to know about weights that are more than 1.3 kilograms below the mean. But this part will be different because this will be 11 divided by the square root of, what's our sample size, 31. So this part will be different because we're dividing by 11 over square root of 31. So this will become, if you flip and multiply, will become this. All right? So in a way, you could almost take what you had, that fraction, and we're multiplying by square root of 31. So this will be, let's see. It's not good to use rounded values in new calculations. You should go ahead and negative 0.66. So that's different, right? Because the distribution of sample means is always going to be a tighter distribution. Will be a closer distribution. Yeah, is there a question here I can answer over here? Yeah? No, did you have a question?
No, I didn't have a question.
Oh, okay. Well, you're talking just keep it talking this way. And
She's asking me a question about the material I'm helping her.
Oh, okay, well, bring it up because someone else is probably having the same question. All right? I'm serious. It's a fact that if you have a question about what's going on with the class and class material, someone else is probably having the very same question, but they're too shy to ask anybody about it, you know? So just ask me and I'll help you out. Okay, just say, I have a question about this or that. All right. Okay, so now, now for this one though, we need to use the other one, right? Yeah, thanks for catching me on that.
Are you okay today?
Huh?
Are you okay today?
I'm fine, I'm good. How are you doing? Good, good. It's good to know. All right, I'm glad you guys are here. You're doing well. Okay. So we would do something like this. I guess that'll end up being the positive of that, right? Yeah, I just wish I had some more help from the class. You know, we're trying to make it where everybody can be learning of quiet, but also have your attention here, and I have to wrangle you guys on the use of technology during class for your class study grade. And I'll let you know though, you know, if you don't like this situation, I guess the first week was when you decided, oh, I don't want to be in that guy's class. I'm going to drop that, but it's a little late now, right? But we'll work it. We'll make it work. Don't worry. I'm here to help you succeed. So, all right. So what do we got here? Yeah, 0.66 again. Of course it is. This is opposite. But really, I'm double checking that I did the calculation right the first time. All right. Okay, so this means that we're going to look for X bar from down.
How did you get 0.66? For any of them, because neither.
Well, because well, 1.3 times square root of 31 divided by 11 came out to be 0.66 because it's 0.658. Yeah, that doesn't mean it's exactly 2/3 or anything because 0.66 is approximately 2/3. But you could say, hey, it's approximately 2/3, right? Not exactly. All right, good questions. I like this question. You'll think that, wow, he doesn't like it if you ask questions because, you know, no, that's how you learn. I mean, that's how I learned. And if something doesn't make sense in class, let me know. Just kind of break right out. I prefer that than, you know, I much prefer that than somebody sleeping or if they're, you know, looking at their cell phone or their laptop. And I prefer, you know, you getting in there and saying, hey, why, how'd you get that number? Teach, you know, let me know if something doesn't make sense. We'll figure it out. We'll work it. We'll, you know, help everybody do well in this class and work to their full potential. All right. at their full potential of figuring out what ads are going on at Walmart during stats class, right? All right. Okay, good. So now we've got this set up. So we have, let's write it down here. Kind of start to see. Oops. Writing too quickly without thinking. My apologies. All right, so we're kind of looking at, it was similar to what we did here in some ways. The numbers are different though, right? It's because the difference between taking a sample of one person and taking a sample of 31 is the distribution, the standard deviation here. And that ends up being a smaller standard deviation, right? And so if you're 1.3 grams away from the mean, that's going to be further away from the mean in terms of standard deviations. That standard deviation of the sample means is going to be larger than this one. See? Because the standard deviation of the sample means is smaller, it's a tighter distribution. So, all right, so we can kind of work it out the same way we did the last one. And we can kind of break this up into a sum of two probabilities. And let's write this down. Let's see if it makes any sense before we buy into it. We'll say, well, these are definitely mutually exclusive events, so the probability that one or the other happens is the sum of the individual probabilities, right? Now this one we can get straight from the table because it's a less than, but here we have to maybe rewrite this as the complementary event. So then we get this number from the table, and then we figure that out. All right, but maybe this will still be one where we end up multiplying by 2 because of the symmetry of the normal distribution table. All right. So let's look at this, negative 0.66, so we look to negative 0.6 down here. And then we go over to the column that's headed by 0.06, and we get, what, 0.2546? Is that right? And make sure everything I'm doing here is correct, because people make mistakes. Sometimes I'll put in a mistake just to see if you're thinking about things that people tell you. I might be telling you something that's wrong, right? Okay, what about less than or equal to positive 0.6? Is that going to be like a complementary number? Complementary with the CONPLEMENT. 0.7454. 7454. We subtract that from 1, I bet we get the same probability as the other way, because of the symmetry again, right? Yeah, I bet that works out that way. 0.25 using the rule of 9s, 46. So if we double that probability, we end up with 0.5092. Am I doing that right? So if you chose somebody off the street, the probability that they're further away from the mean weight, if they're 1.3 grams above or below, or further down below or above the mean weight, is higher than if you get a sample mean and look at it being 1.3 below the sample weight, the population mean weight, or 1.3 grams or more above the population mean weight, 1.3 grams or lower than the population mean weight. And yeah, why would that make sense? Why would that be that way? We talked about how the when we just have a sample of one person, we have it's more spread out. You know, the standard deviation is 11, where here the standard deviation is smaller. So this is a tighter mean. So if you're looking at means of samples of a certain size, then it will be if the size is 2 or bigger, then it's going to be a tighter distribution compared to the distribution of the x values, the individual x values. You can think of each of these x values as being a sample of 1, where these x bars are a sample of, in this case, 31. And that's going to have a tighter distribution. So to be 1.3 down below is further away, relatively speaking. So you're going to be less likely to be further away, 1.3 kilograms below the mean or above. Okay. All right, so we've done some examples for 7.1. Let's go on to get into the next section. But let me know if you have any questions. Just I really appreciate your questions, because that way I kind of know what you're thinking about. I might even realize that I said something wrong that was confusing that I shouldn't have said. And all right, let's go on to an 8.1. We estimating population means. This is where we get into confidence intervals, and this relates to things you probably see in the news all the time, where they have a margin of error and things like that. So, all right, the assignment of values to a population parameter based on a value of the corresponding sample statistic is called estimation. Remember, the population parameter is like the mu that we're often trying to figure out, and by using samples and looking at sample means, and x bar is the sample statistic. Okay, when the mean or expected value of a sample statistic like x bar, which is mu sub x bar, does not consistently underestimate or overestimate the population parameter mu, then x bar is called an unbiased estimator. So x bar is an unbiased estimator of mu. The mean of the x bars, mu sub x bar, is always equal to the population mean. The value of a sample statistic used to estimate a population parameter is called a point estimate. We just talked about point estimates so far. All right, so for example, one might say that the mean housing expenditure per month for all households is $1,970. In this case, based on a sample, x bar equals 1970 is a point estimate for the population mean mu of monthly house expenditures of all households. Okay. In interval estimation, an interval is constructed around the point estimate, and it's stated that this interval is likely to contain the corresponding population parameter. So, for example, instead of a point estimate, one might instead say that the mean housing expenditure per month for all households is $1,970. That was our point estimate, plus or minus $340. In this case, since 1970 minus 340 is 1630, and 1970 plus 340 is 2310, the interval 1630 to 2310 is said to contain the population mean mu with a certain high probability. The number added to the point estimate x bar, which is, in this example is 340, is called the margin of error or maximum error of estimate. Okay, a more general and precise formulation will be good. So here's some definitions. The level of confidence, denoted by C, is the percentage of all possible samples of a given size that will produce interval estimates that contain the actual parameter. So a confidence interval is an interval estimate associated with a certain level of confidence, where C will often be 0.90, 0.95, or 0.99. So when we find a confidence interval at the level of confidence 0.90, for example, then that means if you did similar samples of that same size and figured out confidence intervals, 90% of the time, those confidence intervals would contain that mu that we don't know about. Say mu is something based on a really big number where we can't just do a census. We can't calculate everything. So we're using samples, small samples. So that's what that C will mean. That you almost want to say 90% of the time when you do that process, yeah, that's really what it is. 90% of the time when you do that process using the samples, that sample size, 90% of the time the interval will contain mu. And you could also use a 0.95 confidence interval or 99% confidence interval. All right, so the confidence interval, no, I'm sorry, these are confidence levels. I'm kind of didn't quite use the right terminology here. So these are levels of confidence, confidence level. Okay, so a confidence interval is given by the point estimate plus or minus the margin of error. All right, the confidence level associated with the confidence interval states how much confidence we have that this interval contains the true population parameter. The confidence level is C equals 1 minus alpha times 100%. You can really think of it as 1 minus alpha, but you maybe multiply by 100 also. And so A alpha is the level of significance. And we'll define a little bit more carefully what level of significance is later. For now, we're defining C to be the confidence level. All right, using the standard normal distribution to estimate a population mean, the requirements are the following. All possible samples of a given size have an equal probability of being chosen. That is, it's a simple random sample is used. The population standard deviation, sigma, is known. So we'll assume we know the population standard deviation. And either the sample size is at least 30, n greater or equal to 30, or the population distribution is approximately normal. So these are the cases. Number 3 is the cases when we can use the normal distribution table. It's either we know that the population distribution is approximately normal, or we're using sample sizes of at least 30, in which case the X bars will have a normal distribution. Okay, confidence interval for mu. The C, we define C, the confidence interval for mu is X bar. So this really tells you how to find the confidence interval. You take the point estimate X bar, the sample mean, and add or subtract the product of these two numbers. And so let's talk about what these two numbers are. Well, we know sigma sub X bar is the distribution of the sample means. It's sigma divided by square root of n, where n is the sample size. And z sub alpha over 2 is a z value, like from the z, just like a number of standard deviations obtained from the standard distribution table, table A or B, for the confidence level C, so that the area to the right of z sub alpha over 2 is alpha over 2. That's why they call it z sub alpha over 2. Equivalently, the area to the left of minus z sub alpha over 2 is alpha over 2. So since our tables are set up to give you areas to the left, well, it really will be the same as this. But the z sub alpha over 2 is positive. It's like the number of standard deviations you are from the mean for that interval. Okay, so therefore the margin of error is, which we'll call capital E, is just the product of those two numbers. So Z is like the number of standard deviations, and sigma sub X bar is the standard deviations. That's really kind of telling you how many standard deviations times the number of times the standard deviation for the sample mean, distribution of sample means. That's how that gives you the margin of error. So that sort of makes sense that you would do that. The number of standard deviations times the standard deviations, right? Okay. So then the confidence interval is X bar minus E to X bar plus E. And so mu is in that interval with a C level of confidence, meaning if we do that process over and over, the same sample size and same situation, if C is 0.90, then that means 90% of the time mu will be in that interval. Okay. All right, so to find the Z value, Z sub alpha over 2 for a 99% confidence level alpha is 1 minus C. It's 1 minus 0.99, which is 0.01, or I guess it's really 1%. So alpha over 2 is half of that. Yeah, alpha is the level of significance. I know this is getting into some, it'll make sense when we kind of do some examples. So it's kind of like, here's sort of a picture here where, like here we have Z sub alpha over 2, and over here we have an area that's equal to alpha over 2. And then over here we have another part that's alpha over 2. And here's positive Z sub alpha over 2. And so these add up to alpha. And so it's like you're going to be in the interval. And so, yeah, maybe there's a picture of that. This would be like the C, because they add up to 100%. C and alpha add up to 100%. So this is going to be your, let's see if we can find a picture. We're at 8.1 here. I'll show you a picture from the book. Often these textbooks have really pretty pictures. Yeah. So here's a picture here for 95, 0.95. C is 0.95. We want to, try to find an interval where the actual mu, population mean we're trying to estimate, is in that interval 95% of the time. And over here to the left is exactly what I put there. It's alpha over 2. And if C is 0.95, then alpha over 2 will be 0.05 divided by 2, because we'll have half of the area outside of 95%. Yeah, what's 1 minus 0.95? Yeah, what's 1 minus 0.95? 0.05. And so each of these would be 0.05 over 2, which is 0.025. And so we want to find the Z value that gives you to the left 0.025 if we had C was 0.95. So here's a picture for that one, but we're in our example here, we're looking for 0.90, and that means that if we have 0.90 here in the center, C equals 0.90, then what's 1 minus 0.90? That'll be the alpha, 0.10, right? Because 0.90 and 0.10, they're like complementary probabilities. They add up to 1. So half of 0.1 over 2 is 0.05, right? And then half, if alpha is 0.10 and the other half is over here, that's also 0.05, right? Okay, so we got an area of 0.05. So what we need to do to find the Z values here, let's look up. So we haven't done this before, but let's look up where we'll do it for the negative value. You almost have to do it for the negative value because of the way the tables are set up. We want that little area to the left. And in the table B, the area to the left are big numbers, bigger than 0.5. So we need to use table A where the Z values are negative. Look up the area 0.0500 in this, remember this tableau of, these are like areas to the left, right? So look up the area 0.0500. And right here we have two numbers that are equal distant. We've got one that's 0.0495 and 0.0505. And so what we'll do is, and this is what the book does, we'll find the Z values for each of these and take their mean, since they're equal distant from 0.05. And so that'll be negative 1.65 and negative 1.64. So what's the mean of negative 1.64 and negative 1.65? It's the halfway point, right? Yeah. So if we take the mean of 1.65 and 1.64, divide by 2, we get 1.645, right? And so that's the z value we'll use. That'll be the z sub, I guess in this case it's z sub 0.05. So that's where we get this. So alpha over 2 is 0.05. We need to find z so that the probability of z less than or equal to minus. This is what we already just figured out. 0.005 is equal to 0.005. Oh, wait, I was doing it for 90. My mistake. What was printed here is 99. Actually, what I was doing here, this picture here is for 0.90, and everything I did was right, except it was for 90, right? So this one, all right, let's make sense of what's printed here, because now it's going to be 0.01 divided by 2, right? So that is 0.005, and then this one is 0.005 also. So if we look that up in the book for the table, look up the area 0.005. Oh, now we have two numbers that are the same. It's the same way. It doesn't always happen that way. Just for these two, I think. We have 0.0049 and 0.0051, and those are each 1/10,000th from 0.005. So we'll take the mean of negative 2.58 and 2.57, which is 2.575. And then that's what they did. Notice here they've got, using the table, we get the minus z sub alpha over 2 is negative 2.58 or negative 2.57. So if you take the mean of those, you get negative 2.575. So we'll use that z sub alpha over 2, we'll use the positive one, because our margin of error will always be positive. So this is to be used to find the margin of error E. And so E will be 2.575 times that sigma sub x bar when we find the margin of error. If you have a that'll always be true. That z value will always be the same for any time you have a 99% level of confidence. All right, so in this example, it says the standard deviation for a population is sigma equals 14.8. A sample of 25 observations selected from this population give a mean of x bar equals 143.72. The population is known to have a normal distribution. So they have to put that in because our sample is less than 30. So we have to know that the population has a normal distribution. Make a 99% confidence interval for mu. Okay, so from what we're given before there, our E will be, grab some paper here. The E will be, oh, that's a disturbance, huh? Let's see. Are you able to hear me better now, Emmanuel, by the way? Okay. So here we figured out our Z value needs to be 2.575. The Z sub 0.005. Yeah, so if we wrote this, this would be 0.005 because half of alpha is that. Now we need to figure out the sigma sub x bar, right? So the sigma sub x bar is going to be sigma divided by square root of n. And what's the sigma? 14.8. So we know the population standard deviation. Oh, it could be that the book was on one of the keys there. Yeah. All right, so 14.8, what's our sample size? Is it 25? And that's a nice perfect square, so we can just divide 14.8 by 5. Now let's see, we'll keep this as exact as possible. There's no need to round. And I've seen people do that, where every step they round off, every step, and then by the time you get to the end, you don't know how off you are. So if you can, keep things as exact as possible to the very end, and then you know you got the best possible approximation. All right, 2.96 is the sigma sub x bar. All right, so we put that in for the sigma sub x bar, 2.96, and that'll give us the margin of error. Okay. So we'll have times 2.575. That gives you 7.622 for the margin of error. Yeah, I'm trying to find ways to make sense out of things, and I think about, well, the margin of error is just the number of standard deviations times the standard deviation, right? So it sort of makes sense in that way. And so then our margin of error, not our margin of error, our confidence interval will be given by the point estimate. That was our mean, 143.72, plus or minus the margin of error, 7.622. And that'll give us our two endpoints, right? So confidence interval then will be, so notice I put in the plus, when you add it, then we'll just change that to a minus. We get 136, what's that? Okay. So I think in the online homework, they may ask you for the lower endpoint and the upper endpoint, separate blanks. But so in this situation, if you go through this process using samples of 25 over and over, 99% of the time, mu will be in this whatever interval you get. Is what that means for the 0.99 confidence level. Or you can say this is a 0.99 confidence interval. Okay. And often when statistics are, you see that on TV or somewhere in the news, they'll always look for the margin of error that's off to the side. Then you can see if the difference between the numbers, are within the margin of error, then you don't really know for sure. But if they're outside the margin of error, then you can kind of take that as, I guess it was a snapshot that group of people that day, you can kind of take it more seriously if the numbers are not within the margin of error. Because you can say, oh, the real mean, what they're polling for, the real mean is going to be, really, that's going to be very similar to that if the numbers are. I'm trying to think of an example without getting too political. Say that 66% of the people prefer, I don't know, electric cars. Is that getting too political? and that's a big difference. 34% just regular old gas cars, right? But the margin of error is like something like that, 7.622. Now the difference here is well beyond 7.622. So you can kind of take it. Well, I think more people like electric cars than gas cars. Maybe not exactly these numbers, but you can say it's within the margin of error that more people prefer electric cars than gas cars. So always look for that margin of error. And that's what we're kind of getting into in chapter 8. Okay. All right, so let's look at, this is actually worked out in the notes. Okay. Find the confidence interval. Let's see if it checks with what we did here. We got 2.96 for the sigma sub x bar. Yeah, that's what we got. And z sub alpha over 2 is 2.575. That was the example before, just finding that z value, which was found in the previous example for a confidence level of 99%. The margin of error is then that product, 7.622. All right, good. And then the confidence interval is then given by the point estimation, x bar, the sample mean, plus or minus the margin of error. And we get those two values. But it did say to round to two places. We went ahead and and these are sort of the unrounded values, but then if it says to round to two decimal places, that was the one thing I didn't do. But you can see there that those would round to 0.10 and 0.34. Okay. All right, any questions on that one? Okay, so this next one, let's do like one more idea and problem. Since the margin of error, so this is the formula for the margin of error. If we take this equation, we'll put in sigma divided by square root of n and solve for n, you can figure out the minimum sample size you need for a given margin of error. And so some of the problems will be like that. So if we solve for n here, do some algebra, so we'll multiply both sides by square root of n, that'll get rid of the fractions, right? We have a fraction on this right side. And now divide by e, and that gets square root of n on both sides. Now if you square both sides, that cancels out the square root. Then you get this, that's like the minimum sample size for estimating a population mean mu. Given the confidence level and a standard deviation of the population, the sample size n that will produce a predetermined margin of error e of the confidence interval estimate of mu is this, given by this expression. And it just comes from the formula for the margin of error, which is, once again, the number of standard deviations times the standard deviation. Okay. Where the whole number n is found using this, and then you always round up. You don't ever round down because that'll give you a number that's not quite enough to ensure that margin of error you want. So you always round up. Okay, so a marketing researcher wants to find a 95% confidence. I think we have time just to kind of read through this example. Wants to find a 95% confidence interval for the mean amount that visitors to a theme park spend per person per day. She knows that the standard deviation of the amount spent per person per day by all visitors of this park is $11, so that's the sigma. How large a sample mean should the researcher select so that the estimate will be within $2 of the population? Okay, since sigma is 11, and so we want $2 to be the margin of error, we'll need to find z for a 95% confidence interval. So so this would be a good, if it's a 95% confidence interval, then the alpha is 0.05, and your so you want to find the z so that the probability is less than or equal to the probability that z is less than or equal to your z value is 1/2 of 0.05, which is 0.0250. Now, if you go to the table, go to the one for the negative z values and look up 0.0250. Some of these are in there exactly. Or you just go to the one that's closest. Yeah, here's 0.0250. Now, what z value goes with this area that's to the left? The area to the left is 0.0250. It's negative 1.96. Negative 1.96. So we'll use for the z sub alpha positive 1.96. And so if you put that into that formula, 1.96 times 11 divided by 2, it's just those three variables. You get this. Let's see if that's right now. Yeah, you get 116.21, so we round up to 117. Since 116 is not quite enough for a margin of error of 2, the approximation should use a sample size of 117 or more. So a sample size of 117 or more is needed there. All right, good. All right, so that's enough for today. I'll put up the 7.2 online homework now, and let's see. So Kari Viatora, come talk to me. And Monica Urias and Dominic Rodriguez, not here. Okay, Natalia Pettis. Okay, good. Emmanuel Osum. Yeah, you have to be a person for the class study grade, Emmanuel. Remember, you can make them up. I'm pretty easygoing about letting people make things up. Class study grade. Samantha Monk is here, and Brianna Munoz is here, and Brianna Morrison here, and Mia Morris here, and Jamie is here, Mario Machaka, who's Mario? Not here? Okay, Miguel Martinez, and Emily Martin. Is Emily Martin here? Isaac Lopez. Okay, very good. Hannah Garcia. Good. Ty Garcia. And Angela Franco is here. Diana Flores, not here. And Aaron Flores.
Just go in and let them know you're here.
Juliana Casada here. Very good. Calavates here. And Hector Capistrano here.
And
Good.
even like
Ace
you do it in like
Donovan.
30-minute increments.
And Ana Luis here. And Sophia Bustillos here. Mark Bernard is here. All right. Right here, got a 100%. Oh, yeah. All right. All right.
To give to you because I
Yeah.
don't want to.
Yeah, you could have slipped it under my door. I should have
I
mentioned
think so,
that. It's okay. No, you're good.
You said you needed.
Oh, no, you're the one who's on the team that still needed to take it, and I said I couldn't properly one of the people this morning. So, but I realized that you could take it 12:30 to 2 if that's any better, or 3:30 to 5 would be better. Okay, all right. But it's downstairs, 109. It's on this end, it's like the north end of the hallway, and I'm in 109D. There's a suite of offices. It's on the other side of the hallway downstairs.
Okay.
All
Thank
right.
you.
Sure,
And
sure,
tomorrow, can I come like at 10 to make up hours?
sure. You have office hours 10 to 11 every day.
Thank you.
Sure.
About the extra credits, can I bring the paper for you today?
Yeah, now that you've taken the test, now you can worry about that extra credit thing.
Yeah.
Yeah.
Can I bring to you?
Sure. Or however you want to do it. If you want to fill it out and send it by email, you can just hand it to me. It might be easier just to hand it to you.
All right. That reminds me, I got a question.
What's that?
I saw like